Good evening, everybody. My name is Sven Löschner. I'm studying applied computer science at the University Bochum. At the moment, I'm writing my bachelor's thesis at the chair for network and data security. Together with André Adelsbach and Ulrich Grevler, I'm working on the project that I'm going to introduce to you in the next couple of minutes. I will present you an approach how to make anonymous broadband broadcasts by misusing a satellite internet service provider account. At first, an overview of what you can expect during my lecture. How you can see, there are two main parts. At first, you will obtain an introduction about internet via satellite, what it is, how it works, and so on. After that, we should have the basic knowledge for the second part, where I will explain our approach to misuse a satellite ISP account. At the end, you will have, I hope, enough time, but I think so, enough time to ask questions, which I will try to answer as good as I can. So that's for introduction. Everybody knows artificial satellites. At the moment, there are a few thousands of them out in space. Because you can't see them with the bare eye, people often forget their importance because they can't see them. But if these satellites were gone, we would all realize very fast. Because satellites are specialized wireless transmitters placed in terrestrial orbit for diverse purposes, such as weather forecasting, television broadcast, radio communication, internet access, and global navigation systems like the well-known GPS. Satellites can receive and retransmit thousands of signals simultaneously, from simple digital data up to complex television programs in HDTV quality, for example. Especially in low infrastructure areas, like the one in the picture above. They also provide an interesting alternative for high-speed internet access because they provide high data rates and they cover very large areas with comparably low effort. One big advantage of services via satellites is the big choice of services you can choose from. So you do not buy hardware that you can only use for accessing the internet, but also for receiving radio or television programs. The hardware parts you need are a satellite dish and a digital LMB, which is the head mounted on the top of the dish arm. At least you need a receiving device, like a digital television receiver, or in our case, a digital or a DVB-S card, digital video broadcast card, mounted in our PC. Now at first, a little bit more about internet via satellite. There often comes up the question how the data is filtered or delivered correctly to the person when it is broadcasted. Television broadcasts, for example, are mostly not addressed to one single user, so you don't have to care that much about addressing. But when, for example, a user wants his satellite ISP to send him his personal emails, he wouldn't be amused if anyone else in the satellite's footprint could receive and read these emails. So the trick that is used is mostly a unique MAC address on each DVB-S card. This MAC address is encapsulated in each file header that is sent to the user. This is not the only, but the most used way data is marked and later identified in satellite broadcasts stream. There are two kinds of internet via satellite which must be differentiated. The first form is the one-way variant. In this one, the satellite only handles the downstream to the user, with the outbound data traveling through a terrestrial return, mostly a telephone modem, taking care of the low bandwidth traffic from the user to the ISP. Most users only desire a high download bandwidth, while they would accept a rather small uplink capacity. So this hybrid solution would satisfy their needs. The other form is the two-way variant. Here the user has got a satellite transmitter unit on his satellite dish that enables a two-way communication with high bandwidth in both directions, such as up and downlink. So the terrestrial return is not needed anymore. As a little note, the uplink bandwidth is much higher than the one-way variance one, but it's still smaller than the downlink bandwidth. The big disadvantage of the nice two-way variant is its very high cost, which make this form of internet via satellite only suitable for companies connecting their remote branches to the data network or so. In our work, we focus only on the one-way variant because it is more common, or it is more common for standard users today. However, we want to stress that our proposal is even more suitable for two-way satellite communication, as the ISP has to broadcast all packets via the satellite downlink. To illustrate how the one-way satellite variant works, consider the setting where a user wants to download a video file from a web server. He establishes a small bandwidth dial-up connection to his ISP, e.g. using in Germany an ISDN line, and in order to initiate the download, his request is sent through the dial-up line to an ISP proxy server, which relays the request to the desired destination address. The reply coming from the server, hopefully our requested video file, is rerouted by the satellite ISP so that it will not come back through the dial-up line. Instead of this, it is encapsulated with the user's MAC, or sometimes the IP address, into a signal based on the DVB standard. And this signal is relayed from the satellite, from the ISP's ground station to the satellite. The satellite now, on his part, broadcasts the data back to the user or the users, who is running a piece of software on his PC which completes the TCP communication transparently to the application or the operation system. But due to the broadcast character of the satellite, the signal dedicated for this user can be received by anyone in the footprint of the satellite. This can be done by setting your DVB-S card into so-called promiscuous mode. This means a mode of operation the DVB-S device is able to receive and read every transmitted data packet, not only its own ones. So it is, or it would be, or it is very easy to read files dedicated to other users when there's no encryption. Now, that were all the basics we need for our solution. So here a direct comparison to the graphics shown before. We have a sender who is an official client of the satellite ISP. He wants to share perhaps his holiday video with some friends, our receiver. This receiver is not an official client of the ISP. He only has got a satellite dish and a digital video broadcast, a DVB-S card. So the basic idea means the server pushing the data and a special mark onto the server. For this upload process, he might use any type of connection. After that, he requests the data from his satellite ISP. The ISP relays the data, as he had done before, to the server. And the server now transmits the data again, but with a header modified with our special mark mentioned before, so that this packet can be identified by everyone who knows this special mark, so you can filter for it. The satellite later now broadcasts the data as it also done before, and our receiver now looks for packets with the mentioned special mark. This is the rough scene how it would work. But before getting more detailed, I would like to make a little insertion about what are anonymity and pseudonymity. Both are often mentioned when people talk about things like sharing files over or through the internet. And anonymity is mostly defined as the state of being not identifiable within the set or within a set of subjects having the same attributes. In anonymity of communication, you've got to take care of both sides. You've got the anonymity of the sender and the anonymity of the receiver. In our case, the sender's anonymity set are the online ISP users. The receiver anonymity is much higher because the set consists of every household with a satellite antenna. Pseudonyms in this way are not anonymous. They are often used to identify. So for example, our special mark given with each file header would be a pseudonym. This is just for understanding the following better. So now we should take a look what the whole project should be able to do at the end. We want to send data with probably low costs to a defined set of anonymous receivers. Additionally, we want to protect our files so they cannot be read by other users who, for example, are also listening on the broadcast in promiscuous mode. In our approach, we differentiate three parts: the sender of the data, the server where the data is temporarily stored, and the receiver of the data. Our send-up program, written in Java, has to solve the most tasks. At first, a selected file must be encrypted because we don't want to show our file exchanges to everyone. For this, we used the Bouncy Castle API, especially as provider for our AES cipher. In addition, a unique ID, this is our special mark, must be generated. This should work as our marker. And in the next step, the file gets split into parts, like I guess it was in the animation before. It's split into parts which are adjusted to the size of the payload of one DVB packet, 1,360 bytes. Into the first 32 bytes of each part comes the ID, followed by the part number. After that, data and ID are sent. After that, the data and the ID are sent via HTTP to our server. If wanted, this connection can also be secured, for example, with an anonymous proxy service. To send the files via HTTP, we use the W3C's JWPut class that belongs to the mentioned WinIE network utility API. But that is not all our sender program has to do. It also has to export the key phrase into a Keystore file. The same applies to the ID, which is saved together with the original file name and the number of parts the file was split into. These two exports are necessary for everyone who wants to receive, join, and decrypt our file. At this current moment, there's no key management implemented yet, so the key has to be sent perhaps via email to the wanted receivers, or must be exchanged during an evening at the pub, for example, or I don't know. Now, let's take a short closer look at the server. Our server bases on the W3C's Jigsaw web server. At first, it stores incoming files and manages the appended IDs. So when there is a file request mostly from an ISP, the server is able to mark our file's HTTP header with our associated ID. That's all our server has got to do, so it's not that much as the sender has to do. Last but not least, we've got our receiver, and here it was a little bit more complicated because Java doesn't get the possibility to access a hardware device directly. So we used the JPCAP class package that makes use of the libpcap and the raw socket API, and together with the Java native interface, we could access the C code of the libpcap and so access our wanted network device, the DVB-S card. So, in simple words, after this implementation, we were able to listen on the satellite broadcast in promiscuous mode, and we were able to search for to filter for our wanted ID. the wanted ID is imported from the emailed or another way delivered ID file. If a packet with our ID is found, it is automatically written on disk, and after the part is stored, the program compares the number of saved file parts with the number of total file parts, which is also told by the imported ID file. And when all packets are received, the parts can be joined together and the file or the files can be decrypted with using the also imported Keystore file. So at first, how we want to extend or what were our first problems or what are possible problems and what were the ways we tried to find solutions. The first problem we found was that there could be a possibly high error rate. That means that some parts get lost or are damaged so that the receiver cannot join the files together. When this would happen to a normal receiver or an official client of the ISP, like our sender, then he simply would re-request the missing packages at his ISP and they would be sent through his return line. But our anonymous receivers don't have a uplink connection to the ISP, so they cannot report a lost or a damaged file part. To prevent this, it is advisable to control the whole transmission also by the sender. So when he doesn't get all packets or he receives damaged file parts, then he could re-request them, but not as an error. He just re-requests the whole file part, so it's not sent through the terrestrial return line. To detect these defect file parts, we try to use, for example, a CSC method. Additionally, the request could be done automatically several times, because the possibility of one and the same data packet getting lost several times or multiple times is rather low. But we also should not forget that, especially in case of satellite broadcasts, interferences can have very local origins, like clouds, thunderstorms or so. From a little futuristic point of view, you could also implement methods to check the actual weather dates at the receiver's position and estimate his specific packet loss rate or so. So you can do if you want. But another real problem, so the high error rate was in our test wasn't a real problem anymore. Another problem could be the linkability. So this was in our first test. So users could try to reuse old IDs to capture new transmissions which are not addressed to them by our sender. To prevent this, we generate, as mentioned before, a long unique ID, 16 bytes long, for every single file exchange. So it's very improbable to have success by listening with an old ID. A little bit more complicated could be a provider-side encryption. In this case, our sender would use a proxy-like software provided from his ISP, and inside this piece of software is the decryption key for this user. And every time the user requests some data, it is encrypted by his ISP. The only suitable solution for us would be to extract the decryption key out of the provider's software and to share it with the receivers, which should be possible because the decryption key is in the software at the user's PC, and it's not changing very often. Another another interesting point would be the anonymity of senders, or to improve the whole anonymity. Therefore, we need multiple senders who upload different files to our file server. After that, they do not request a special file, but a random one. This could also be realized server-side by sending a random packet on a specific request. If someone uninvited would be listening on the whole broadcast, he would try to join the packets of one specific user, but these packets would not all belong together because their common bond does not based on the user's MAC address as normal, but on our ID hidden in the file header. To illustrate this scenario, we've got the same components with additionally two other video file parts or other file parts on the server. Our holiday video is again split in parts, into 4 parts, I guess. Yes, into parts. And it is again sent to the server. After that, the sender requests some common packets which are rerouted as before from his ISP to the server. The other things are also at first the same. But now our receiver sees only the file parts of the correct video. He doesn't see the red ones because his part of software is filtering for the correct ID, unconcerned of the destination MAC address, which is normally important for identifying your files in the broadcast stream. But if there would be now someone else listening, he would, for example, see there are 4 packets delivered to our sender. He doesn't know anything about the real receivers. But these 4 packets with our sender's MAC address are not the correct parts of our holiday movies. There are, for example, 2 parts of the red file and 2 parts of the real movie. So he would only see some garbage data he couldn't join or even decrypt. So what are the next steps we want to take? At first, we're going to implement some methods for better analysis. That means, for example, a visualization of the file parts you're missing, or a statistic of how many packets are received during the first pass of sending, how many packets need 2 pass or more pass, and how many packets get lost, and so on. Another important aspect will be the exchange of the key and the ID file, because it would be very nice to provide an integrated solution additionally to the one exporting the file and exchanging it in a pub, or I don't know where. Additionally, the graphical user interfaces must be extended, just as ways to improve the sender's anonymity should be implemented in a more full way. So far, I guess, yes, that's all from my side. At first, I'd like to say if someone is interested to help in this project or wants some information, you are welcome to contact us via email, for example. And I'm now open for answering questions if someone has one or more.
Hello? Okay. Would it be possible to just share bandwidth by relaying the request from the receiver to over the person with the ISP account, and then filtering the packages which are sent to the person with the ISP account, and
Yes.
filtering them. That's simple. Would that not be possible?
You want to know if it is possible to filter the packets that are shared from the sender, or what?
Yes. Well, basically, you would use the person with the ISP account as a kind of proxy server, and make him request a file, and then filter out the package, the packets which are going to him from the satellite.
You want to know if this would be possible?
Yes.
The main goal was to improve, at first, anonymity of the receivers. So this would be possible to use the owner of the satellite ISP account to use him as a proxy, but this is not the main goal. Mainly he should.
Okay, it's not the goal. Okay,
No,
but
and
it would be possible in theory.
mainly, yes. I guess it would be possible.
It could.
It could be possible. Yes.
Is it possible to change your MAC address to upload some data from an account of another user using ISP?
To fake the MAC address.
Yes.
Yes, possibly you can do that, but you've got the problem. The upload progress is not anonymous when you are not using.
Yes, but if it is both way.
If it is both way, it would be possible if your ISP would allow your MAC address, because normally the ISP is looking for the MAC address. Is he in my allowed list? And if you find a user and you fake his MAC address, yes, it would be possible.
Uh-huh.
Isn't the data sent by the satellite provider encrypted anyway for privacy reasons? And this would be a problem for your approach, wouldn't it?
This is interesting. Yes, if it is encrypted, it really is a problem. But there are two aspects. At first, there are still many providers who don't encrypt their broadcasts.
Which providers do not encrypt?
Net systems, for example. So this is the biggest I know. Yes, the encryption. There's another point. You can also receive these files because the decryption key is into the software proxy the user who wants to receive the files has to use from his ISP. And it is possible to extract this decryption key and share it with other users. So they just need to install the proxy software and import the key. So they would also be, so yes, they could also decrypt these files.
Okay, but does this make the filtering process more complicated?
No, it does not, because just a moment. If you've got this case, then you would have the proxy software of the ISP in front of the whole receiving progress. There you would filter the data for this user, and after that it would be sent to our software, then it is decrypted, and there you could again search for our ID.
Okay, so only the content is encrypted and never the receiver ID.
No, it's everything encrypted, but the decryption progress is before the search for the ID. So at first, the proxy software decrypts it, and then the whole the whole files or the whole stream that is now decrypted is given to the searching part.
Yeah, I wonder if you got any information about satellites which are out of service. Actually, I got a story about a guy who phoned over voice over IP from the South Pole via a satellite which is not normally working for the ISP, which is just abandoned, but it's still in the orbit, and it's like it's traveling there, and it's function, and people can use it to have a TCP/IP connection over it. So maybe you got information about this too.
Sorry, but sounds very interesting.
Yeah, to me too. But there was a guy at the Off the Hack radio show who just called from the South Pole, and he claimed that they use satellites which aren't normally anymore used by the companies, but ran on the orbit all the time, and you can use them for this stuff here. Maybe you can try to investigate in this. Yeah.
I've got one question. Concerning the ISP side, is it possible to detect from the ISP if somebody is listening on their and putting the cards in promiscuous mode?
No, that's not possible, because it is a passive connection, or not a real connection. It's like the connection you have when you're receiving a television program. You have just a receiving device. Most of these receivers only need a receiving device. They don't have any uplink to the provider, so you can't see if someone is listening in promiscuous mode.
Did you ever try to send unrequested data to an IP address of a user of such an satellite?
We are just testing this with net systems. I guess this is the system we're testing on. I guess it's a problem. So we used the way that that the server selects random packages himself and sends them, so that the sender requests, the sender requests a specific packet, and the sender says, yes, I give you this packet, but it's not this packet you want. So it's a little bit tricked.
So you can't just ping the IP address and the ping goes over the satellite?
No, I just don't want to say no, but
The idea would be to send UDP broadcasting data like RTP video streams to an IP address you don't own, but which is on the satellite provider, and broadcast your television program without paying anything.
I guess this would make some problems, but I'm not 100% sure. So sorry, can't help you on this one.
So the receiver is in promiscuous mode. Why do you not just use the MAC address of the originator? Why the artificial ID?
If we would use the promiscuous mode, is the only, or is the easiest way to access data that is sent to other MAC addresses other than our own ones. Because normally, if you're listening on a broadcast stream, you're only receiving the messages for your own MAC address, which is onto your hardware. So you've got to use the promiscuous mode to access other MAC addresses.
Hello. The question was, actually you are in promiscuous mode and you get the whole packets. And you're filtering all the packets for the artificial ID, which you introduced.
Yes.
So why not just filter for a MAC address of the...
Yes, this would be also a solution, could even be a little bit quicker. It's just, we've at first said the only information we want to give to our receivers is only this specific ID, so that they don't even want to try to receive later transmission from the same sender, because perhaps he wants to send the mentioned holiday video to his friends, but to his girlfriend, he wants to send a few photos or so, but he don't want his friend to receive these photos too.
But if you do it always from the same MAC address, it's obsolete, I guess. So the first time I have the artificial ID, I know the MAC address, so I'm continuing sniffing for this very MAC address.
Yes, you could continue sniffing from this MAC address. This is why the last mentioned send anonymity would be more interesting, or would disable this function. In the first variant, yes, you could do this, and it would be even more suitable to use the MAC address. But if the server is sending random packages, then you can't filter for the MAC address, because if you're filtering for the MAC address, you get data garbage.
Thank you.
Okay. Then thank you for listening and have a nice day.